In this video, we are going to talk about factor groups and also about normal subgroups. So let's start with normal subgroups. As we sort of saw last time, sometimes when we look at the left or the right cosets of a particular subgroup of G, it has this beautiful property that if you arrange the Cayley table according to that subgroup, with the rows and the columns, that it will sort of chunk the group up into these really nice colored squares. And that was a sort of desirable property, and we were attempting to determine what is it about a subgroup that makes that happen. As it turns out, that subgroup needs to be what's called a normal subgroup. And the property that we need is for that particular subgroup that we're going to denote by n, and we're going to use this little triangle to denote normality. It needs to be the case that all of the left cosets are precisely equal to the right cosets for all elements of G. Now note that this is not quite as specific of a requirement as it seems originally, requiring that these two sets, AN and NA, are equal for all A and G is not the same as requiring little a times little n to be equal to little n times little a. We're not requiring that elements of A and N commute. What we are requiring is that for all AN, which would be an element of the coset little a times n, so we can take that element little a little n and write it as k times a, where k is some possibly different element of n. So we'll see an example of this as we go on, but it's not quite as strong as requiring elements to commute, but it is actually this weaker hypothesis. Of course, if it is the case that all elements of a group commute, and little a times little n is little n times little a for all a's and n's in the group, then, so having an abelian group, then certainly the subgroup will be normal, but it's not a requirement. And the example we saw last time was that the subgroup of rotations inside of Dn, we were using D4 as an example, but the subgroup of rotations happens to be a normal subgroup of Dn. We'll see why in this video. And we know that D4 is not an abelian group. So the group doesn't need to be abelian. You don't need element-wise commutators, but what you do need is this little an times little ka. So let's begin with an example. Let's show that the subgroup n, which is the identity, the permutation 1, 2, 3, and the permutation 1, 3, 2, that's a subgroup of S3, but let's show that it's a normal subgroup of S3 using the definition. If we go to the Cayley table and compute our left cosets of this subgroup in G, so the way we've been doing this is listing the elements of the subgroup for left cosets. We list the elements of the subgroup across the top and the elements of the group going up and down. So for the rows and the columns are the elements of the subgroup. If we go through and use the Cayley table and do this computation, we notice that the left cosets of n in S3 are our original subgroup n and this other coset. I'm denoting it by 1, 2, n. That's this set of transpositions, 1, 2, 1, 3, and 2, 3, as a left coset. If we change our point of view and all of a sudden say, let's now compute the right cosets, so let's list the elements of the subgroup as the rows in our Cayley table and use all group elements as the columns, we can compute the cosets this way as well, and we get the same collection of elements. One collection is the subgroup n, and the other collection is this set of transpositions, 1, 2, 1, 3, and 2, 3. Those are the same sets as the left cosets, and so this is an example of a normal subgroup. What I would like you to notice, though, is let's pick an example. We've named this other coset as 1, 2, n, or this one right here should say n, 1, 2, because I'm thinking of it as a right coset. Let's write an element. Here's an element 2, 3. 2, 3 belongs to this other set, the coset 1, 2, comma n, or n, comma 1, 2. However, in the left cosets, if we go back here, the element 2, 3 belongs to that, but it is viewed as 1, 2 multiplied by the element of n, 1, 3, 2. That's the way that I obtain 2, 3, thinking of it as being part of this coset. So 1, 2 multiplied by 1, 3, 2 in the left coset gives me 2, 3. If I move on to the next right coset and I look for the element 2, 3 as it appears in this coset, it actually comes about as being the element 1, 2, 3 multiplied by 1, 2. So yes, 2, 3 belongs to this left coset, which is the collection of transpositions, and it belongs to the right coset, but it's not the case that that an is equal to na. If we were going back to the an is equal to ka, then the n for the left coset would be 1, 3, 2, while the k for the right coset is 1, 2, 3. So different elements. Now we can generalize this previous example quite a bit. Let's suppose that we have an arbitrary group, G, and we have a subgroup N that happens to have index 2. Remember that the index of a subgroup is the number of left or right cosets of that subgroup inside the larger group G. So what this means is there are 2 left or alternatively right cosets. For the left cosets of N and G, that is, we're always going to have the subgroup as one of our cosets, so N will be a left coset, and then there's some other left coset, let's name it AN, for some A and G. Similarly, we have 2 right cosets of N and G, so N has to be one of them, that's always a coset if it's on the left or on the right, and we'll name the other coset N times little b, for some B and G. I'm using a different letter because I don't know where A belongs. In fact, I do. Let's think about this a little bit further. Let's start with G, an arbitrary element of the group big G. If it happens to be the case that G belongs to N, then N by itself is both a left and a right coset. So these cosets, left and right cosets, N and N, have to be the same. They're outright equal. What if we start with an element of the group that doesn't belong to that coset? So it doesn't belong to this coset over here. It has to have a home. And there's only one other place it could belong. It has to belong over here, to AN. Similarly, for the right cosets, it doesn't belong to N, so that element A has to belong, G, has to belong to this right coset NB. This proves that this set, AN, has all the same elements of G as this set, NB, proving that these 2 things are equal, and these 2 things are equal. If the left and right cosets are equal, it has to be a normal subgroup. As a corollary of this, you can deduce that some of our favorite subgroups that we've been studying are in fact normal subgroups of the larger groups to which they belong. So for example, AN, the group of even permutations, is a normal subgroup of SN, and the subgroup of rotations in DN is normal in DN. If you think back to our very first example that we did, working inside of S3, this is actually the example we did. We took a look at the identity, which is an even permutation, and we looked at 1, 2, 3 and 1, 3, 2. Although those are elements of odd order, remember that they can be written as an even number of transpositions. So the subgroup we were looking at in the first example was A3, and we proved that it was normal in S3. But we can actually do better just generalizing the thought process there. We're now ready to move on to the definition of a factor group. So let's suppose that we have a group G, and let's identify its operation as dot, the way we have been doing. And let's assume that N is a normal subgroup of G. Then the factor group, or some people say the quotient group G mod N, is equal to the set of cosets where we range over all elements of A and G. That set of cosets forms a group under this new operation that we're going to call star, where we take 2 cosets, AH and BH, let's say AN and BN, be consistent here, and you combine them by taking the representatives, A and B, and combining them under whatever the original group operation was, and then looking at that coset. As an example, I said we say out loud that this factor group is called G mod N. That notation is meant to be indicative. It's meant to remind you of the integers modulo N. We have this relationship between the integers and the integers modulo N, where we felt like we have this really close relationship between those 2 things from the very start of the course. we were sort of tempted to say that maybe the integers modulo n were a subgroup of the integers, and they turned out not to be, but the precise relationship that we want there between these two groups is that the integers modulo n are a factor group of the integers. Additionally, we've seen that a group somewhat similar to z mod 2z, 0 and 1 together, is a factor group of Sn. That's the factor group we've been looking at. It's Sn mod An. Because we're going to have two elements of that factor group, even permutations and odd permutations, it's going to sort of be like the remainder when you divide by 2, 0 or 1, even or odd. Just as a computational note here, if n happens to be a normal subgroup of G, then left cosets are equal to right cosets for all little a and g. That's our definition. What's often computationally more helpful is to use this alternative and equivalent condition that a subgroup n is normal in G if and only if A inverse is equal to n for all a and g. Now, let's take a look at properties of the factor group. We're asserting that a factor group is in fact a group. In order to be a group, this set of cosets, it needs to be closed under the operation that we've defined. That seems sort of clear. We've defined the product of two cosets to be a cosets, so closure seems free for us. But it should satisfy the other group theory axioms. It should have an identity, should have inverses, and the operation should be associative. The identity of G mod n is the subgroup n. And if you think about it, hopefully that should make sense. The coset that serves as the identity is the coset that contains the original group's identity. Similarly, if you're looking for inverses, if A is an element of G, then the inverse of the coset that contains A is the coset that contains its inverse. Now, associativity is something we basically never check because it's quite tedious. But what's secretly sneaky about this is that we have something else to check too, besides just the four group axioms. We made a definition that we would take two cosets and combine them by taking the named representatives, combining them, and then looking at that coset. But cosets have many names. An has many different coset representatives, and if C is a different member of An, then they have the same coset. An is Cn, because cosets are either totally disjoint or they're precisely equal. But on the one hand, we've taken An and said we need to combine that with Bn by looking for the coset that contains A dot B. If we instead changed our point of view and thought of An as Cn, we would say Cn needs to be combined with Bn to be the coset containing C dot B. I need to check to make sure that this operation I defined is in fact well defined, so that I'm not taking two cosets, trying to combine them, and then sending them to different places. They always need to get sent to the same place. So the thing that we have to check is that the definition that we made makes sense. So really what we want to do is say, let's suppose that C is an element of the coset An, and we've defined A dot Bn. We want to check that we have made a well-defined operation that we're going to send these to the same places. So if you go back, we want to check that this coset and this coset are the same. The way that we're going to do this is we're going to say they're cosets. They either are entirely disjoint, or if they overlap at all, they must be equal. So we're going to pick our favorite element of the coset A dot Bn, which is A dot B, and we're going to show that it belongs to the coset C dot Bn. That will show that there's some overlap between these two cosets, and by properties of cosets, they have to be the same. So, because An and Cn are actually the same coset, that means that the element A belongs to the coset Cn. And we can take A then and write it as C dot n for some little n in n. Now, when you look at A dot B, we substitute in C dot n for A. We have C dot nb, and by associativity, this is C dot n dot b. Next, let's use the fact that n is a normal subgroup of G. That means that the left coset, Bn, is equal to the right coset, Nb. making sure that we're using the right condition for left cosets being equal to right cosets. This means that we can take n dot b, an element of this right coset, nb, and we can write it as b dot k for some k inside of n. Switch it around and think of it as the left element of the left coset. Hence, if we put all those things together, substituting in all the right spots, a dot b is c dot n dot b, switch your parentheses by associativity, and then substitute in b dot k for n dot b. Now, use associativity again and switch that around. Think of this as c dot b multiplied by an element of n. That will be a member of this coset c dot b times n. Thus, cosets with a non-trivial intersection, this coset a dot bn and this coset c dot bn, they have a non-trivial intersection, they have to be equal, and our operation is in fact well defined. To check your understanding, this is going to be a take-home quiz that I'd like you to complete and turn in to me at our next class period, is to perform the following example. So the first thing I'd like you to do is explain why, if I have the subgroup just one containing 1 and 4, let's explain why that's a normal subgroup of the group U of 15. Because it's a normal subgroup, let's just determine the cosets, not left or right, just cosets, because they're the same, of n and g. Then, complete a Cayley table on pencil and paper for the cosets of n and g using the definition of the operation in a factor group. And last but not least, we want to check that this all lines up with our motivation. We want to check that if we took this subgroup, computed the cosets, and made this colored Cayley table in Excel, that the factor group structure that we're doing on pencil and paper actually matches with the group structure we'd be seeing in that colored Cayley table. So after doing the procedure and making the Cayley table on pencil and paper without any colors, create a colored Cayley table for the factor group in Excel and check that these things match up and have the exact same structure.